am an assistant professor at SUNY Oswego in our computer science department. I've been there just about 2 years. Excuse me, I'm finishing up my 4th semester. So I like it a lot. The winters haven't been too terribly scary for me up there. We had a lot more snow last year than we did this year, but it's all seems to be quite manageable. But the department up at Oswego, I'm really glad that I ended up there. We are doing a lot of interesting things. We're growing the department. We have a new major in software engineering now, and that's really why I was brought specifically in to staff that faculty. We are also revamping our human-computer interaction master's program. So if you know of any students that might be interested in that, that is a nice transition once you've gone through our CS program. So there's a lot going on up there. As Dan also mentioned, I did my Ph.D. at Purdue University in West Lafayette, Indiana. While I was there, I was a member of the Sirius Security Research Group, the Center for Education and Research in Information Assurance and Security. Sirius is about 10 years old now. We were the first major information security research center of its kind in the United States. And my faculty advisor up there is a gentleman by the name of Gene Spafford, who is a very highly regarded professional. Spaff is a member of our executive board at Rome and sort of guides our programs there. Interestingly, a lot of people may not know about Gene is that he was actually instrumental in discovering immunities to the first internet worm that appeared in the late 1980s, the Morris worm. And he was a relatively new faculty member at Purdue when he started up there when this thing broke, but it was he and his team of students that were actually able to figure out what was going on and get that remedied. I am very, very glad to be here to speak to you all today. This is something that I enjoy doing very much, and that is getting together with people who are teaching in high schools and teaching students who are interested in things like computer technology, computer science, computer security, and so forth. The reason that I like doing this so much because I firmly believe that the time that we invest in having these sort of interactions pays off for everyone involved. You get students who are more engaged. We get better prepared students. In other words, literally, the students that you have today are my students of tomorrow. And anything that we can do to help them, give them a leg up in the program is something that I'm happy to do. So I'll do workshops like this around the country through the summer. I have one in Milwaukee that I'll be doing in a few weeks, another out in West Lafayette. And so I want to again thank you for taking the time to come out and hear me talk today. What I'd like to talk to you today about is a very important subject as it relates to the internet as we know it today. I'll talk a little bit about some historical context, but what I'm really focusing on is the future, and that is a whole new way of thinking about how we're going to provision the internet using a new protocol called IPv6. Now I say new protocol, I'll elaborate on that why I think it's new, but it has been around for quite some time. It's just that it hasn't gotten into people's consciousness until relatively recently. We're going to be doing a lot of exercises today that'll actually give you some visibility into what IPv6 is, what it looks like. This is an outline of what I'm going to be talking about today. Any talk that's introducing some material is going to have to start with some terminology. So we'll start with that. I'm also going to talk about IPv6 addressing. It differs greatly from the IPv4 addressing that you're probably used to. One of the most important things that is introduced into the use of IPv6 is something called neighbor and router discovery. This is a collection of protocols that fundamentally change how IPv6 addresses are assigned. We will talk about the details of that, but this is something that anybody who is going to talk about IPv6 should be telling you about, because this is where things are really going to be different. IPv6 provides some changes to various headers and header fields, and we're going to talk about that. And then we're going to wrap up in talking about some specifically security-related headers that this protocol provides for us. And then we'll have some time for summary and questions and answers and your feedback and so forth. Okay, so let's start with a little terminology. These are some terms that I'm going to be just throwing out over the course of the morning, and it's a good idea that we have some foundation or some grounding in what they actually mean. I'm going to talk about protocols. There's lots of different protocols out there. It's a bit of a misnomer to call IPv6 a protocol because that's a collection of many protocols that are bundled together. So when I say protocol, well, what is that exactly? Well, you can kind of think of a protocol as a definition of how two entities would communicate with one another. I'm speaking English right now, and as a result of your education, your cultural immersion and so forth, you can understand what I'm saying. You know, we have a protocol that defines how the English language is spoken, and because we sort of understand how that protocol works, we're able to communicate with one another. If I were to start speaking another language, some of you may not be able to understand what I was saying. Or if maybe I was speaking the English words, but I just started mixing them up in all different ways. You know, if you ask me a question like, well, what does this IPv6 header do? And I would say, my shoes feel really tight right now. You know, you would think, well, that's strange. And what does that have to do with what it is that I'm trying to find out? So think of protocols as sort of agreements that entities have with one another that define some ways that we're going to communicate. And they're oftentimes referred to as languages, you know, as sort of the language of communications that computer systems that would then use to exchange information among one another. Okay, so we know what a protocol is. An attribute is something, you can think of it as a value or an entity or quantity that helps the protocol operate. So protocols have different attributes to keep track of basically what the protocol is doing. An example might be, if I'm going to send you a message, one of the attributes that I would provide would be the destination address of where I want the message to be sent. Or another attribute might be, if I'm sending out a packet in the network, how many different routers is this packet permitted to traverse before it's discarded? That's an example of another attribute that is used to support a given protocol. Now, you'll sometimes hear these things referred to as fields, and that's typically when you're looking at the actual traffic itself, and we say, okay, this field has this value, this field has that value. What they're really talking about are attributes that define how this protocol works. And then finally, we have something called a value. And of course, a value is, it's like a number or a quantity that you assign to a given attribute at a given point in time. So if I going back to the example of the source and destination addresses in a packet, those can have different values, and the values that they have define where that particular message goes. Or they might define what state the protocol is in. In other words, I've made an initial contact and you have responded and so forth, and we have attribute values that convey that. So protocols can have attributes, and attributes have values, and the values that they have define what the state of the protocol is at any given point in time. So that's the relationship among those three. What I'm guessing that most of you are familiar with is a protocol called the IPv4 protocol. And the IP part stands for Internet Protocol, nothing fancy there. The V4 stands for the particular version of this protocol that was created. This is the protocol that defines the Internet that we know it today. It's been around for a long time. A lot of people don't realize that the Internet Protocol version 4 was actually created in the late 1970s and formalized in the early 1980s. So this protocol has been around now for almost 30 years. Clearly, it wasn't until the early to mid-90s that it became sort of a cultural phenomenon, that people had the World Wide Web, we had email, now we have mobile devices that are taking advantage of this network and so forth. But it has been around for a good long time. And that's an interesting sort of side note to bring up. When the protocol was written in the late 1970s, early 1980s, there was a really very different notion of the purpose that this particular protocol would provide. It was thought that, oh, okay, well, we're going to have some quantity of computers that are around the world, and basically this will be sort of a fairly tight-knit federation. People who operate these things will know each other. They will trust one another. They will have conversations outside of the internet space to describe how things should be put together and so forth. It's basically a community of people that trust one another. Well, clearly, they did not anticipate the way that the internet was going to be used even 10 or 15 years later. And that's actually one of the reasons why we had to start thinking about what are we going to do next, because clearly IPv4 has some limitations that we'll talk about in a moment. IPv4, just like every other protocol, has this collection of attributes that defines how the protocol behaves. The protocol is designed specifically to allow communication among networks. That's a misconception that a lot of people have. They think, well, I'm running the IP protocol between computers. No. The IP protocol is designed to allow networks or communication across networks. We have other protocols that allow people to just communicate locally and so forth. Hosts, these are the individual computers that are on the system itself. We designate those with a 32-bit quantity, also sometimes called a 4-octet quantity or a 4-byte quantity, that defines the address. So every computer, every host that's on the internet has to have a unique 32-bit number that differentiates it from every other computer on the internet. And here's an example of something like, for example, if you have a DSL type service or a broadband service at home, a lot of people have home networks that allow you to set up multiple machines. And this is a network ID, 192.168, that you oftentimes see among people who are using systems in such a configuration. This would be the IP address for a given computer on that network. This I'm guessing that many of you have not seen. This is what's called the header, or the attributes that are wrapped around data that is sent over the IP protocol looks like. This is called the IP packet header, all right? And you'll see that what it starts off with is a 4-bit quantity here that is called the version field. And this defines what version of the IP protocol that you're running. Now, clearly, it should be 4, right? Because this is IP version 4. So typically when you look at IP traffic, IPv4 traffic, this value has a value of 4. We then have a 4-bit quantity that defines how big this header is. In other words, how many bytes are occupied here. I'll come back to that in a moment and talk about why that's important. But for the time being, let's skip ahead a little bit and take a look here. This is our first address. It's a 32-bit value, and this is the source address. So the computer system that is actually sending the packet, they populate this attribute with their address. The value below is the destination address. So this is where we want the packet to go. Also a 32-bit value. Now there are some other things that it would draw your attention to here. We have something called the time to live. Now the time to live is an 8-bit value, and basically this holds a value that says how many routers can this packet go across before it's discarded. The reason that we have this value is, let's say that I have a packet and I want to send it off to someone, but I don't quite know what route it's going to take to get to them. So I send this packet off, and it traverses one router and then traverses another router, and hopefully it's making its way toward the user. But let's say that something happens that causes the routers to reconfigure themselves such that we end up with a loop in the path somewhere. So if the packet happened to be unfortunate enough to get into that loop, it would go on, it would just keep getting passed around forever. Unless we have a mechanism like this that says every time you encounter a router, you decrement that value by 1. So eventually that packet will get passed around until its time to live reaches 0, at which point it gets thrown away. So this is specifically here to keep packets from clogging up the network that never go away. Now, there is another length field here called the total length. And the total length field includes all of this header plus all of the data that is included in this packet. Because we don't, this information, these attributes here, all they're doing is trying to get the data from one place to another. The data itself that is going to be used by the application is living down here. So in order to calculate what the length of the data is, we have to take this total length and subtract from it the length of the header. That tells us how much data is actually being sent. All right? So it's an additional step there. There's another field in here that bears some explanation called the checksum field. Checksum. Has anybody ever heard the term checksum before? Okay. Checksum is a way of sort of telling that or determining that the packet hasn't been damaged in some way along its transmission. Because it's possible, you know, you send a packet up over a satellite link, maybe there's some clouds or turbulence or some sort of interference, and one of the bits gets changed, right? So is there a way to detect that? And so the checksum field is a sort of a stamp that the packet gets. You compute the checksum, you put it in the packet gets sent off. When it reaches its destination, we do the checksum again just to make sure that it's still valid, it still matches. If it doesn't, then we know that the packet is corrupt in some way and we should throw it away.
You would ask for input if anything jumped out at us about students
Right.
earlier on.
Right.
So I don't mean to disrupt the flow. But,
No.
Last year I ran it by Kevin and Dan. We were talking about a good activity for cybersecurity or HTML is how protocol might work. I said I would take a packet of index cards. I mean, I don't even use the word packet.
Yeah.
A big chunk of index cards.
Yeah.
And I would try to send a message through a classroom full of kids and where they're all acting like routers.
Yep.
And it would be jumbled, and I would try to send them to multiple students so they have to understand they should be establishing a protocol. What does
Right.
it mean if, you know, somebody left the room and it's looking for them? They should be dealing with the time to live kind of thing.
Right.
There should definitely be a destination kind of address. There should be a sender. How do they know it's from me? How do they know to put it back in the right order? How
Yep.
many messages there are?
Yep.
You know, how many note cards? And hopefully they would establish themselves some kind of protocol, like a list of rules that they should put together a complete message so they know they have everything.
That's an excellent idea. And in fact, it's funny you should mention that because I do precisely that thing in one of my workshops. I take slips of paper that have, you know, an address on them and a message and so forth, and each person becomes a router, and they have some very simple rules on what it is that they have to follow. And I think that would be a great exercise. I don't actually have them derive a protocol, but I think that would be a wonderful thing to do.
I guess would be to have them enforce some of these kind of rules. Oh,
Exactly.
Time to live, you know, what if the person left? Well,
Yeah.
we should keep track of how long it's been.
That is an excellent idea, and thanks for bringing that up, because this is precisely the sort of thing that I would like that we share amongst one another. So, but as Matt points out, what we would like people to, as they're studying this, is to be able to look at these fields here, or these attributes, whatever you want to call them, and be able to assign meaning for them. Why are they there? Why are they useful? You know, we talk about why the checksum is useful, why the time to live is useful, and so forth. But there are other fields in here like the identification field. You know, every IP packet has a unique identifier. Now, as it turns out, there is a very important reason why that's there, but at first you might look at it and think, well, why do I have to number every single packet? What good is that? I mean, because it isn't the idea to get the packet from here to there anyway? Okay, the one last field that I'd like to draw your attention to is this 13-bit field here called the fragment offset. The IP protocol has a feature built into it called fragmentation. And what fragmentation is supposed to do is, let's say that you send a packet out to someone, and it is traversing through some networks and ultimately gets to a router, and that router decides, okay, well now I'm going to send it out on this particular link to this host. But the packet that you've given it is too big to put on the underlying network. Every underlying network technology has a capacity for the size packets that it can handle. So you've given me a packet, I know where it has to go, but it's too big for where you want me to put it. It's like if I sent you a package in the mail and you insisted that all of your mail was put inside your mailbox. So what if the package doesn't fit in there? What am I supposed to do? I'm supposed to just, rip it open and, maybe I can take the thing apart and cram it in there, or maybe I take the packet and put it some other place. Or maybe what IP does is it throws the package away, or throws the packet away and sends you a message that said, hey, that packet you sent me was too big. I have to fragment it. So that's what IP does. It actually takes the packet, breaks it up into smaller bits, and then sends it over the network such that it can deliver it. I bring this out because this field, the fragmentation field, the checksum field, the length field, are all different in this new version of IP. So it's important that we understand what these parameters or these attributes are doing now such that we can talk about them coming up. You may be asking yourself, well, hey, listen, the internet works great. I mean, I get all my YouTube videos and I can Facebook anytime I want, and it seems to work great for me. Why do we need this new protocol? Why is everybody so concerned about it? Well, people who have been working in this field for a while actually began to have some concerns about IPv4 almost 20 years ago now. And it actually had to do with the fact that when we assigned IP addresses to people, we just don't assign one address per person. We typically would assign a range of addresses as belonging to a particular organization. And so let's say that you're Syracuse University. You go to the body that actually distributes the IP addresses and you say, I want to have 10,000 addresses. That's how many computers I anticipate having on my particular network. And they say, okay, well, here's the forms that you have to fill out to get those addresses, and here's the address range, or here is you could think of it as the prefix that you would append to all of your addresses. So now whenever we see an address that starts with 128 dot whatever, we'll know that that's Syracuse University. But here's the problem. When Syracuse University or Purdue University or whatever organization actually requests the addresses, they typically overestimate how many they're going to need. And so when you order them, let's say that you order 10,000, but at the peak of their use, maybe you're only using 40%, 50% of them. The problem is that those remaining 50% can't be used by anybody else because they all have that prefix that defines them as Syracuse University, Purdue University, and so forth. So they're wasted. There's a lot of waste in the IPv4 address space. A lot of people have requested a lot of addresses over the years that they just can't use, that they're just not using. Now, over the last 10 or 15 years, they've come up with some interesting strategies on how we can sort of improve and not waste so much. But the fact is that we have a lot of legacy systems, a lot of legacy assignments that we can't change. So for example, like in your broadband service at home, when you order up service from the cable company or from Verizon or whatever, you don't get an IP address for every system that you have in your house, like for your DVR box and for your PC and all your laptops and so forth. You get one address, and that one address is shared among all of the devices in your home, right? So that's a way to sort of combat this this waste that we've been going through. But we knew that eventually what we would have to do is we'd have to increase the size of the address, because as we'll see in a moment, 32 bits really doesn't give you a lot in terms of the pure number of hosts that you can have. So there was a big debate for a number of years. People said, okay, well, what we really need is a 64-bit address. Let's make it twice as big as it is now. All right? That seems like it's a reasonable value. And then other folks said, oh, no, we need 160 bits, because we would like to have all of these variable addressing schemes, like some addresses would be short and some addresses would be long. So we need a really, really big space. Let's throw it 160 bits. After all of the dust had settled, they decided on 128-bit addresses. So this new IP version 6 protocol differs significantly from IPv4 in that we have 128-bit addresses as opposed to the old 32. There was also a general move toward enhancing the efficiency of routing of packets. So we want packets to be able to be routed more quickly. And because we said in the original internet design, where it was a nice community, everybody knew each other, everybody trusted each other, that turns out not to be such a good assumption. We're going to put a lot more focus on security now. So things like making sure that packets are authenticated as coming from a particular place, making sure that packets are encrypted so that we can't read their contents. And so the Internet Engineering Task Force, the IETF, in 1998 they named this new version of IPv6 what they call the next generation protocol for the Internet. So now IPv6 is what, for the last 10 or 11 years now, is what we know eventually we're going to have to migrate to at some point. So one of the first questions that I get from students when they're talking about this, they say, well, okay, we go from IPv4 to IPv6. They say, well, what happened to IPv5? Did it just disappear? No, what happened was IPv5 is a real protocol that it's an experimental streaming protocol for things like video that someone came up with, and it turns out not to be that useful. So it's just going to consume that version number forever, and we're just going to go move ahead and stick with IPv6. So that's why we skip from IPv4 to IPv6. 128 bits, that's a big number. That's a lot of addresses. That's a big space. Just to give you an idea of how big that is, if you have 32 bits, you have 2 to the 32 different unique values that you can compute with that, or different values that you can have. So that equates to roughly 4.4 billion different systems. Now, back in 1981, people said 4 billion computers on the internet. Wow, that'll never happen. That's crazy big. Nobody will ever get that large. And well, it wasn't too long when they started to figure out, well, wait a second, what if every person had a computer? There's more than 6 billion people on the earth. Or what if we had multiple computers for every person? Or maybe we could have 10 computers in every home. It starts to add up. A lot of people, though, think that we maybe went a little bit overboard with the 128-bit addresses, and this is why. So if you have 128 bits, you can have 3.4 times 10 to the 38 different addresses. Let me put that in perspective for you. That gives you 6.7 times 10 to the 19th addresses, which is a huge amount, by the way, for every square centimeter of surface on the Earth. So you take every square centimeter of surface on the Earth, including the ocean, and you can place 15 billion current IPv4 networks in that little space. I do not think that IPv6 addresses are going to be running out in the next 20 years, let's say. Now, if we start,
space travel really takes
unless we start putting IP addresses on Pluto and Saturn and all of the Mars, the moons of Jupiter and so forth, we'll have to start worrying about it. For the time being, I think we're good. If we've got 128 bits of addressing, clearly we're going to have a different scheme for annotating what those addresses look like. You remember the IPv4 is what we call dotted decimal notation. There is 4 decimal numbers indicating each one of the 32 bits. So the way that we write these is we now write them in 8 groups of 4 hexadecimal digits each, or 2 bytes, 2 octets, whatever you want to call it. So this is a real IPv6 address. I don't know what it is, but I did find it in one of our traces, so I know that it exists. So each one of these values here that's separated by the colon is actually a different collection of 2 bits or 2 octets. All right? And it's typically listed in hexadecimal notation. So if you're familiar with that, you know, a single digit goes from 0 to 9 and then A, B, C, D, E, and F. Right. Now, this, I think you could agree, this gets kind of big, right? I mean, 128 bits, and you've got these 8 collections of 4 bytes each. So there are some shorthand notations that you can use to actually shrink this down. One of the things that we can do is we can drop all the leading zeros that exist in an address. So I've highlighted them or bolded them to correspond to the bytes that were changed. So this 0 now corresponds to here. This 0 corresponds to this collection of zeros. This 0 corresponds to this one. I dropped the 0 from the FAB, and now it's just FAB. And I dropped the zeros from the 1, and I just now have 1. So this is a little bit easier to read. Now, even that wasn't enough for some. People say, well, you know, why do I have to have 8 groups? Why can't I have something less if I've got nothing but zeros in the middle? So you do have this additional thing called the double colon substitution. And what you can do there is put 2 colons together, and that just indicates an arbitrary number of zeros that exist between these 2 quantities. Now the thing is about the double colon substitution is that you can only have 1 in an address. You can't have more than 1. Would you like to offer a suggestion as to why you can't have more than 1? Like, why can't I got this 0 here. Why can't I just make that a double colon?
Because you wouldn't know how many zeros each.
That's exactly right. So this very important value here could shift anywhere between these other 2 values, and we wouldn't know precisely where. So that's why we can only have 1 substitution exactly. Okay, so this is what an IPv6 address looks like. Pretty long. Now an IPv6 is typically split up into a collection of different components. What we'll do is we'll take this 128 bits and we'll split it in half, right down the middle. The lower half we'll refer to as the host ID. So the lower half corresponds to a given host, and the upper half, what we're going to do is we're going to call that the ID of the network itself. So we can have 64 bits defining the network, 64 bits defining a host within that network. Still, a tremendously large number of hosts and networks that we can provide. Now, what we'll do, though, is we'll take the network ID and we'll actually segment that again a little bit more so that we can provide something called the subnet. And what the subnet provides for us is a way to differentiate different networks within an organization. Let's say, again, assume that this is assigned to Syracuse University. Syracuse should say, okay, well, this highest order n bits, we're going to use to designate that as Syracuse. So if you see any address on the web or on the network that starts with these n bits, you know to send it to Syracuse. Now once it gets there, Syracuse will then examine the remaining 64 minus n bits to determine what network it belongs to. And once they know that, then they can route it to the appropriate network. And once it's on the appropriate network, that router can use the host ID to figure out precisely which host it belongs to. So you see how that works? Are you familiar with this idea of classes with IPv4 addresses? Have anybody heard that term before? Okay, well when IPv4 addresses were first assigned, they were assigned in what's called a class structure. So you would have a class A address would define the first octet as being one address. A class B address would be the first 2 octets, and so forth. And that actually contributed to a lot of the waste that I was talking about. If you assign someone a class A address, that means that nobody else in the whole world can start with that first octet. That's a lot of addresses that could possibly be used by other people. This is similar, but we solved the problem of the waste because first of all, we have this gigillion sized space of addresses, so we're really not as concerned about the waste as we used to be. But secondly, the IPv6 address space is said to be a contiguous address space, meaning that you can assign a big range of addresses right next to a small one. You don't have to divide things up into this class setup the way we used to. Now, one thing that I didn't mention is that you can actually use what's called the MAC address, the media access something. I don't remember what the C stands for. Media access control address to actually construct the host ID. Now, when a computer comes online, when it becomes active, its MAC address is actually burned into the hardware. So it knows its own MAC address. And that means that computers can actually create, with a little bit of help, they can create their own IPv6 addresses all by themselves. I want to talk a little bit more about the different types of addresses that you're going to encounter when you're looking at IPv6. There are 3 basic types. The first one is called the Unicast, and a unicast, as the name implies, is a communication between one host to another host. It's one host sending information to another host. So I'm specifically naming not only the host that I'm coming from, but the host that I want to connect to. And these are what are said to be globally routable. So a unicast address that goes out onto the internet should be able to identify a specific host anywhere in the world, anywhere on this particular network. You can identify unicast networks by looking at the first 3 bits of the address. If you see 001, you know that that's a unicast address. If you see anything else, it's not a unicast address. There are many different types, but those particular bits are specified for unicast. Now, multicast is also a type of address that you can find in IPv6, and multicast has actually been around for a while. We have multicast addressing in IPv4 too. It works slightly differently, but the general idea is that a single host or a single computer can send a message to a multicast address. And what that will then do is be delivered to a group of hosts that all essentially subscribe to that multicast address. So let's say that you're a movie studio, and you want to deliver a digital stream of a new motion picture directly to a group of theaters that you own, like Sony Pictures, for example. Well, what they could do is they could set up a multicast address, and all of the theaters then subscribe to this multicast address, and then Sony just has to send out one stream, and that stream effectively gets duplicated. Those packets effectively get duplicated and sent to multiple locations. So we are delivering to an entire group of hosts that belong to this address. And as I said, that's been around for a while with IPv4, they just do it a different way. There is a new type of address that is initiated with IPv6 called the Anycast address. And this is actually a pretty cool idea. The Anycast address is similar to the multicast in the sense you send a packet off to what you believe is a group of people that are all subscribing, but you're effectively saying, hey, I've got this request here and I want it to be satisfied, but I don't really care who satisfies it. Any one of you group of people, if you respond to me, I'll be satisfied. So it's a way of delivering a message to someone, but I only care about one person, or I only care about, let's say, the closest person responding to me. Now, if you think about that for a minute, that's a really great idea for things like mobile devices. So I've got a mobile device, and let's say that I bring it into this building. I don't know anything about the networks in here. My mobile device doesn't know anything about the networks. But the mobile device can say, hey, I've got some information here, and I want to send it out to the closest machine or the closest router that can get me out on the internet. And I don't care who it is. Just take care of it. And if you do is set it up in this Unicast format, it'll work. Right? So it differs from the multicast in the sense that I don't have to send it to an entire group. I'm only interested in somebody who can help me. I want to spend a little bit of time talking about these multicasts in more detail because we're going to see some examples of it in the next lab that we do where we take a look at actual multicast address transmissions. And so again, we say that a multicast address identifies a group of hosts that all want to receive some information. These start with the octet FF. So if you see any address on the network, they're going to start with the first group, 2 octets, is going to be FF. There's also a flag here in this flag section that indicates whether or not this multicast address is supposed to be transient or permanent. Typically, these things are transient. They're in use for a while, and then they're not in use anymore. There's actually 4 flags in this field that 3 of them we're not using right now anyway. They're just reserved. But we may have uses for them one day. Now, the scope is something that is important to talk about. So the next 4 bits of the address indicate the scope of this address. So the scope of this multicast. And there are various different levels of scope that you can have. So if I'm only interested in multicasting to hosts that are on my connected network, that's called a link scope. If I'm interested in communicating in a multicast fashion with other networks in my organization, let's say all of the networks at Syracuse University, then I would use something called a site scope. Right? So I'd want to span different networks. And if I'm interested in doing multicasting that could reach potentially anyone in the entire IPv6 internet, I use what's called a global scope. Right? And we'll take a look at those values. So here, like if you're using link scope, the value is 2. If you're using site, the value is 5, organization 8, and 14 for global. So this is an example of what I was saying a little bit earlier, where the value that a particular attribute has defines how the protocol works. So this says, all right, if I have a link multicast address, a multicast address with a link scope, I only want that to be operating within my local area network. I never want to see that address outside of my network. That would be bad. And as a router, what I'll try to do is filter that so that it doesn't happen. Now this is a big change for IPv6, and I want to spend a little bit of time on this before we jump into the next lab. When we had IPv4 we still have IPv4 for these nearly 30 years now, we needed some what they call underlying protocols or link layer protocols to help us do some matching between what the internet address was, like say 192.168. whatever, to a local network address. Every computer on a local network has to have a uniquely identifiable address. But we don't want it to be the same uniquely identifiable address that we use to differentiate all PCs in the world, all computers in the world. So there had to be some protocol that would provide us this matching. And in the old days, what we would use is something called ARP, which is the Address Resolution Protocol. So ARP would work in the following way. I'm an application, and let's say that I want to reach a web server that I know to be on my local area network. I would send out a request to say, hey, I want to reach the following web server, and here's its IPv4 address. Somebody tell me who that is. And this message would go out to the whole network. Say, hey, if you are the following person or the following entity, send me a message back and let me know. And so what you would see is an ARP request, this message going out to the entire network to say who is so-and-so. And then an ARP reply would be that particular entity saying, oh, that's me, and here's my address that you want to use. So ARP was used for a lot of things. It was used to help a particular host find out who the other machines on the network were. And it was also used, again, to provide this mapping between the network address and the IP address, the things that the application would use to communicate. The thing that's different about IPv6 is that we have taken these functions that used to be in this link level protocol and we have moved them into IPv6. And you might ask, well, why did we do that? Well, there's a couple of different reasons why we did it, but primarily we did it so that we could incorporate some of these enhanced security features that we've been talking about earlier. So let's go back to the ARP example for a minute. Suppose I send out a request that says, hey, I'm looking for a certain computer on the network. And some bad computer or some malicious person has their computer to respond and say, that's me, when it's really not them. It's really not the computer that I expect to communicate with. Well, what does that mean? Well, that means that I'm communicating with somebody who is masquerading as someone else. And that could be bad. I could reveal information that shouldn't be revealed. I could allow them access into my machine when they shouldn't have access to it. So it's problematic, right? There was no mechanism for actually identifying or authenticating an individual or individual system as that person who they claim to be, or that system that they claim to be. IPv6 does have mechanisms like that. So now, if we wanted to, we could actually say, all right, here's a request for something, and if we get a reply back, we can examine that response a little bit more clearly to find out, is this person or is this entity who they claim to be? We use this idea in a new protocol that IPv6 uses called the Neighbor Discovery Protocol. And as the name implies, what we're trying to do is we're trying to discover information about other systems, other hosts that are on our network. And this idea is to incorporate the features and functions of these underlying link level protocols into IPv6. And IPv6, the Neighbor Discovery Protocol, actually makes a lot of use of these multicast addresses that we talked about a moment ago. And it does so in a very clever way. It also uses something called ICMP v6. Does anybody ever heard of the term ICMP before? Does anybody know what ICMP stands for? Internet Control Messaging Protocol. So things like ping. When you ping a particular host, that's an ICMP message. When a router sends you a message that your packet has been dropped because the TTL value has gone to 0, that's an example of an ICMP message. So these are messages that are sort of informational. They tell you things about the network, they tell you things about other hosts. So with a combination of these IPvcast multicast addresses and ICMP v6 messages, we can perform effectively the same functions and in a better way than we used to with this combination of IPv4 and ARP. So here are some of the things that you can actually learn about your neighbors through this network discovery protocol. We can learn about other hosts on the network. We can do address resolution like we used to do with ARP. We can find if an address is duplicated. So I can send out a message that says, hey, I'm thinking of using this address. Does this belong to anybody else? And that person or entity will respond back saying, yeah, it belongs to me. It's duplicate. You can't use it. We can determine whether or not particular neighbors are unreachable. So something has happened to them, their machines have crashed or whatever, the network connection has been severed for some reason, we can't communicate with them. And we can figure out what the next hop for a given packet is. So I get a packet, I realize that I can't service it, I have to send it off to somewhere else. I can query the network to say, hey, where should this packet go next? I can also get information about the routers, and this is something that wasn't available in ARP, but is available in IPv6. I can actually discover routers, so I can enter the network and say, hey, who's a router that can transmit my traffic to the internet. And assuming that there is such an entity, it will respond back and say, yeah, that's me, send it here. I can determine what the network prefix is. Remember a few slides ago we talked about how a v6 address is partitioned. Half of it is the host address, the upper half is the network address. Well, I can actually learn what this network prefix is from the routers themselves. They'll tell me that. I can learn other network parameters, and we'll talk about some of those in a little while. And I can do something called auto-configuration, which is really, really cool. Auto-configuration basically says, I'm a new host on a network, I learn some parameters about the network, and I can create an address that allows me to effectively communicate with anyone without actually asking for anything. I just get the information I need to configure myself. So these are the different ICMP messages that you'll see when you're using the network neighbor discovery protocol. We have a neighbor solicitation, which is, hey, do any of my neighbors fit the following criteria? And if so, your neighbor will respond back. Neighbor advertisement is a message that comes in response to the solicitation. So I said, does anybody have this? So hopefully somebody will reply in the affirmative. You also have router solicitation messages. So you send out a message saying, what are the routers on this network? And then a router advertisement. So a router can periodically will send out information that says, I'm a router, here's information about the network, just in case you're interested. And then one that is that we're probably not going to talk about too much, but you should know about, is the redirect message. So let's say that something happens to the router on the network. The router, if it identifies a particular type of problem, can send out a message and suggest that people update their routing so that they stop sending it to one router and start sending it to another. That can be useful. I've alluded to this a couple of times, how hosts can configure themselves in this IPv6 world. And we talked about the MAC address before, how the MAC address is a address that is burned into every hardware interface that you buy. It's burned in by the manufacturer. It is not something that can be changed easily, but it can be changed if you know how to do so. So it's something that you keep in mind. It is not an absolute, in other words. If somebody shows you, oh, I've got a MAC address, you say, well, you know, we know those can be modified, but let's just assume that it's very difficult to do that. So we have this MAC address that, again, is burned into every interface that's produced. It contains some information that identifies the manufacturer, and then some more information that identifies the sort of serial number of the interface itself. So this is the first interface built by Cisco. Here's the second interface built by Cisco, the third and fourth, and so on. And the manufacturers are obligated never to duplicate MAC addresses that they've used in the past. But the fact that we have a fairly reasonable amount of trust in the fact that this MAC address is a unique value, identifying a specific interface, why don't we use that to build an IPv6 address that we also want to be unique in the context of the internet? So this is how it's done. MAC addresses are 48 bits long. So what we do is we take the MAC address and we split it in half. So we have 24 high order bits, 24 low order bits. And then we take this special collection of bytes here and we stick it in the middle. So we put in the middle FFEE. And then, so that gives us, this of course is 2 bytes. So now we have 50 bytes for the MAC address plus this thing. And now we're going to append this prefix onto the network ID. This indicates something called a link local address. So you can kind of think of this as an address in the IPv6 world that differentiates this host from every other host on that link or on that network. And they all start with this prefix FE08. So if you ever see that, that's known as a link level address. It is used to uniquely identify hosts on an IPv6 local network. Now, here's a kind of a tricky thing. Sometimes, not all the time, but sometimes we take, so we got, this is a little bit confusing, I'm going to try to explain. So you got this 50-bit value, right? That was the MAC address with this new thing inserted. Sometimes what we do is we count off the 7th highest order bit. So 1, 2, 3, 4, 5, 6, 7. And then we flip that bit. So if it was a 0, it's now a 1. If it's a 1, it's now 0. And that forms a specific type of address called the EUI something unique identifier -60, modified EIU64 address. Sometimes we see that and sometimes we don't. But it really doesn't matter a whole lot, because what we're trying to do is we're trying to create something that's unique in the context of this link. And assuming that this is unique, what's derived from it should also be unique, right? If they're all derived in the same way. So let's take a look at an example of how we do this. So I can start, this is in a hardware address, a MAC address that came from a real interface. As you can see, it's got 6 bytes, 8 bits each, so that's a 48-bit quantity. I'm going to split it in half, right? And then I'm going to insert this FFEE in the middle of it. So now I've got these 50 bits right across here. And that represents at least the beginnings of the network portion. And now I'm going to prefix this with this FE and a bunch of zeros afterwards. So my new link level address then becomes FE, bunch of zeros, and then this 50-bit quantity that we've derived. As I say, sometimes we will take the 7th bit, counting from this leftmost one, and flip it. So if it was 0, it becomes 1. If it 1, it becomes 0. And so this could become C00054, because we flipped the 1 that was in the bit position corresponding to that value, that a byte value of 2. So it becomes 0. But again, it really doesn't matter a whole heck of a lot, because what we're trying to do is come up with something unique for this link. And assuming that this is likely to be unique, we also have some special addresses, multicast addresses, that we use when we're doing this neighbor discovery protocol. The first is FF02. Remember, we said that all multicast addresses start with FF. So FF and 02, does anybody remember what the O2 stands for? Link scope, right. So this is a multicast address within the link, within the scope of the link. We don't want this to leave our local area network. So if you see this FF02, a bunch of zeros and then the last bit 1, last value number 1, this is a multicast address saying, I want to communicate with every host on this network. If you see this one, FF02, this says, I want to communicate not with every host, but with every router that identifies itself. So this is kind of a cool idea, right? I'm in this network. I've just joined this network. I don't know anything about it, but I can send a message to this address, and I can get a response back from all of the routers that are on the network. We realize that we live in a world that we can't transmit IPv6 traffic the way that we would like to, but what we can do is we can take IPv6 traffic, encapsulate it in IPv4 traffic, and then send it out over this IPv4 network. And then once it gets to its destination, it becomes IPv6 again. I'll try to fit that in before we go. All right, now this is really cool right here. The solicited node multicast address. So this is a little bit tricky, but I want to see if I can explain how this works. So remember when I talked about how ARP, when I would want to find out who on the network had a certain address, I would send out a message to the whole network and I'd say, hey, which one of you has the following address? Now, if you had tens of thousands of hosts on the network, you're bothering a lot of other hosts that are not going to respond to you. I mean, because it's only going to be one that you're looking for. So why bother everybody else? So what IPv6 has created is this thing called the solicited node multicast. And basically what this means is it is a way to segment out a much smaller pool of candidate addresses to which you can then send a multicast address. And the multicast address, this solicited node multicast address, is actually created from the lower 24 bits of the IPv6 address, plus this fancy prefix right here. Right? So what this says is, okay, I'm going to create a multicast address derived from some IPv6 address, and for all intents and purposes, there's only likely to be one other address in this thing. But it's possible that there could be more, but it's unlikely. So now, if I want to find out who has a given address, let's say an address that I'm interested in using, I don't have to bother everybody. I just have to bother a small group of candidates who are likely to have this address. And that's what the solicited node multicast provides for you. We said that neighbor solicitation is one of the types of messages that are being sent out by IPv6, ICMP v6. Its message type is 135. You'll see that when you look at the scans. Now, when we're doing a neighbor solicitation, basically what we're asking is, does any of my neighbors currently have this address? And maybe it's an address that I'm interested in using, right? I'm trying to come up on the network. I've looked at my MAC address. I've figured out, okay, well, I can construct this local link address from it. Let me see if there's anybody else who has this. Unlikely, but I should check. So I send out this message, but when I send out the message, I send something called the unspecified address, because I don't know that I can use it yet. But I need to check first. So I just send out this address that has all zeros as the source. But look where I send it. I send it to this solicited node multicast, because again, I'm not interested in bothering everybody. I'm only interested in asking the people that are likely to have the same address that I want to use. That's a really nice feature. So then if I wait for a little period of time for someone to respond back with a neighbor advertisement, and if nobody does, if nobody says, hey, that's me, you can't use that address, then that's the address I'm going to start using. Here, I don't know if you can see this too well, but here's a collection of traffic that correspond to this neighbor discovery protocol. So you'll notice the first message is here. What's the source address for this message?
0.
It's all zeros. It's that unspecified address that we were talking about, right? So this entity doesn't yet have an IPv6 link local address. It doesn't yet know how to identify itself. So what it's doing, what is it sending to here? What's that?
That's its new address, if it can accept it.
This is, yes, this is the multicast, the solicited node multicast for the address that it wants to use. So if someone else has this address, they're going to be using this same solicited node multicast. So this is the person this is the entity or the group of entities to send this to. Maybe somebody there is using it. So this is my neighbor solicitation message. Now, how much time has elapsed between these two packets?
10 to the second.
Not quite.
No.
You got 0 and 9/10.
Yeah.
So almost a second has elapsed. So this host sends out this neighbor solicitation that says, hey, solicited node multicast, are any one of you using this address that I might want to use? And nobody responds for nearly a second. So they say, okay, well, if nobody says it's me, then I'm just going to use that. So look what it does. The next packet that it sends out now has its link level address, unicast address that it's created. And we can't see all the fields now, but if you were to examine this, you would see that you get these bits, you put in that FFEE in the middle, and then you have the remaining bits, the remaining 24 bits on the other side. Where's this going? FF02 1.
It's a link node to everybody,
That's right. It's a multicast address to
all the computers around.
every computer on the network. And what is it saying?
It's just basically saying, here I am, this is my address.
This is me, right. I am announcing myself as one of your neighbors, and this is my address. All right, what's it doing here?
Right.
That's right. So not only is it announcing itself as a host, in the next packet it says, oh, and furthermore, I'm a router. If this message were only targeted to other routers, it would be going to the other, but it's going to everybody. So even if there were another router on this network, we now have another one. We have somebody else who has announced themselves as a router. This is the solicited node multicast address. The packet is being sent to that, and basically this packet is saying, hey, I want to use this address for myself. Is there someone who is part of this multicast address who has that? And so we can, again, come down here into the ICMP v6 portion of the packet, and look at the target, and we see F080, bunch of zeros, C00054, blah, blah, blah. What I want you to see is, do you notice, first of all, here is the first half of the MAC address, here's the second half, and we put that split FFFE right in the middle. You see that? Right here? So this is actually, oh, and by the way, the bit was flipped.
Yeah, it was, because the 2 went to a 0.
That's right. So it was formerly a 2 and it went to a 0. So now this is a modified EUI64 address. That, again, that the host created on its own. It didn't, and it created this, and it's asking, hey, does anybody else have it? Again, the packet or the interface is announcing itself as a router. So first it's saying, hey, does anybody have this address that I want to use? If no, then I'm going to start using it, and I'm going to tell everyone that I'm using it. I'm doing that with the neighbor advertisement. And then I'm going to go one step further and say, I'm not only your neighbor, but I'm also a router. I don't think we talked about this, but one of the things that you can learn about a network from these router advertisement messages is the network prefix. Remember we mentioned that? So if I go to the router advertisement and I take a look at, I'm going to make this bigger so we can read it. I take a look at this, see this line right here that says IPv6 option prefix information? If I expand that, look what I get. That's my network prefix. So if I have a link level address that is unique, I can append it with this network prefix corresponding to my network, and this is given to me by the router. I then have a global unicast address that I can use to send packets all over the world. So what is going on here is that the router's interface basically took that network prefix, added it onto its network address, its link level address, and converted it into a unicast address. And now it's announcing that to the network. It's announcing it is a neighbor, but this is my unicast address. Does everybody see that?
So that was still the same machine.
Still the same machine. And the reason that I can tell that, of course, is if I go down to the source address right here, the Ethernet source address is still
The same MAC, yeah.
CC20054 blah, blah, blah. It's the same machine, but this is the sort of the cool thing about IPv6. It's the same machine, but now we are giving different advertisements for different roles, if you will. I've got an address that I can be referred to just within my own network, and now I've got another address that I can use to send packets outside of the network. But it's the same machine, same interface. What does it mean for an IPv6 message to have a hop count of 1?
Goes directly from one machine to the other.
Right. What would happen if that packet were to somehow traverse a router?
Hop count would increase.
No, it'd be
It would decrease to
0.
0, and which would mean what?
It's dumb.
We'd throw it away.
Dump it.
So this is a packet that what? Can never leave our network. If it does, it's going to be discarded. So what kind of packets are these? Well, let's see. If we type IPv6, and the only reason I know this is because I looked over many of your shoulders. IPv6 dot, what is it, lim, hop count lim,
Double equals,
equals what?
double equals, oh, you got it.
Right, double equals 1. Apply. So what kind of messages are these?
Multicast listener report.
These are all multicast listener reports. We didn't talk about this too terribly much, but the multicast listener report is another sort of multicast address that is collecting information about the whole network. So if you send your address to the multicast listener report, it basically updates some cache that says, oh, okay, here's another host, here's its address, and it just keeps this sort of global list for everything. What I will ask you to do, perhaps when you get back to your school, is to try this next lab where you actually dive into the IPv6 header a bit more deeply and look at some various values to find things. I talk a bit about here about the checksum field, the absence of the fragmentation. I'll just mention that very quickly. IPv6, if you remember in the IPv4 header, we had the checksum field, which we would use to identify errors in transmission. We had the fragmentation field, which we would use to take a packet, break it up into smaller bits so that we could deliver it. And we've gotten rid of those for IPv6. And you might ask, well, why did we do that? Well, the reason that we did it is because if I don't have to do a checksum and I don't have to worry about fragmenting packets, I can make my routers a lot more efficient. They can process packets much more quickly now because they don't have to do these calculations anymore. Now, there are some trade-offs, as there always are, but the thought is that, for example, if we get rid of the checksum, what will that mean? Well, basically what it'll mean is that the supporting protocols, things like TCP and UDP or the Ethernet protocols, they'll have to pick up the slack as it relates to finding error checking. And they do. They all have those checksums built into them. So the IPv4 checksum was kind of seen as redundant, and it really wasn't that effective anyway. So if we get rid of it, it's not a big loss. Fragmentation is another matter, though. And fragmentation fundamentally changes a certain way that the internet used to work. The way it works now is that if I were to send a packet and for some reason it can't go across a particular link because it's too large, the router would just handle that for me. It would split up the packet, it would send it off, and then it would get reassembled at the distant end. As far as I was concerned, nothing weird happened. The data that I wanted to send got there. Whether or not it got fragmented on the way, I don't care. As long as it gets to the destination, I'm fine. Because IPv6 doesn't have, or well, let's put it this more accurately. In IPv6, routers no longer do fragmentation. They simply discard packets. If you get a packet, if a router gets a packet that's to deliver something and it's too big to go on that underlying network, it throws the packet away and sends an ICMP message back to the host and says, the packet you sent me was too big. Send it again and send it in, and this time send it in a smaller size. Now, of course, what does that do? That puts now the onus on the hosts themselves to try to figure out, well, what size packets can I send so that they don't get fragmented? And again, in IPv6, we've taken some of these low-level functionalities and we've built them into IPv6. So now there's something called the Message Transfer Unit Query, or MTU. So you can ask the router, hey, what's a good size packet that I should send for this network? And the router will tell you that. So it'll say, okay, well, I can handle 1,500 bytes per packet. And that's what the host should use. Now, that's no guarantee that once the packet leaves that network that it's not going to be dropped by some other network. But at least we have some sense of where to start. The smallest packet that IPv6 can handle is 1,280 bytes. So if you always send the minimum size packets, you can be guaranteed that they'll go through. But, people get greedy. They want to send more stuff. So what they'll do is they'll send a 28 or a 1280 packet. That goes through. Let's double the size. See if that goes through. Let's double the size again. See if that goes through. If that doesn't go through, well, then maybe we'll throttle it back a little bit and try to send something slightly smaller until we find out where the sweet spot is. But then again, there's no guarantee that that's not going to change. Some link could go down, the route gets changed around, and before you know it, you're actually going on some completely different path that has a different MTU. So it's probably good that we're skipping over this because there's a lot of protocols to try to figure out what the optimum size message is for a given path that's really beyond the scope of what we're talking about here. But the important thing to remember is, take away from this is, there's no more fragmentation at the routers when you're doing IPv6. I want to spend the last few minutes talking about some optional headers that really give IPv6 a lot of power. Now, if you recall, way back in the beginning, we said that when IPv4 was written, we had a very different notion of how the protocol was going to be used. We had a very different notion about the users themselves, what kind of information would be on it. Did you know that up until the early 90s, it was highly frowned upon to have commercial traffic on the internet? If someone found out that you were doing something in a commercial endeavor, that was really, really looked down upon. I mentioned a few moments ago that routers in IPv6 don't do fragmentation anymore. But that doesn't mean that they don't have fragmentation. It just means that the routers don't do it. The hosts do it, and the way that they accomplish it now is through an actual separate header that handles specifically fragmentation issues. There's also another header that will handle specific routing options. So let's say that you have a collection of packets that you want to give some special attention to. And there are a variety of different options that you could have. But let's say that you wanted to have them routed in a certain way or monitored in a certain way. You could specify that in a routing options header, and IPv6 will handle that for you. But the last two are the ones that really give IPv6 the jump over IPv4. IPv4 had no mechanism whatsoever to determine whether or not a given packet coming from a destination was that particular destination. Today, I could sit down on my computer and I could start sending out packets with the source address of Microsoft or Amazon or anybody else, and there is little in the way of protections to prevent me from doing something like that. What IPv6 does, though, is provides this new header called the authentication header that allows you to actually authenticate a given packet as coming from a particular host or interface. And that's a very powerful thing, because now when I get a packet from you, I can authenticate you, and I can say, yes, that is in fact who I believe the packet is coming from. Now, that's all well and good, but it doesn't really give us much in terms of privacy, right? I mean, I know that I'm communicating with you, but if somebody were eavesdropping on our communications, they would see everything that we're talking about. So what this next header does, the encryption header, is allows you to take information, encrypt it within IPv6, such that anybody who is monitoring the transmission, unless they have the keys to decrypt things, would not be able to see what it is that you're sending. The authentication header and the encryption header are part of something called IPsec. Actually, IPsec is a separate protocol that was written for IPv6, but they later found that they could adapt it to IPv4 too. So you can find it in both contexts, but it was really designed specifically for IPv6. Basically what happens is this is a set of protocols that allows two hosts to negotiate things like what authentication algorithms we're going to use, what encryption algorithms we're going to use, what kind of keys we're going to use. And once we have decided on that, we can communicate with one another in a secure fashion. As I mentioned, here are the two, the authentication header. So we can guarantee the identity of a particular sender, and the encapsulating security payload, or ESP, actually encrypts the packet. It actually also provides some levels of authentication too. Here is what happens when you are using an authentication header with an IPv6 packet, also referred to as a datagram. So this is what the original packet looked like, right? I have my IPv6 header here. right? So this has things like the source address, the destination address, the hop limit. And then here is the data that I'm sending. Now this data happens to be TCP traffic, transport control traffic. So this might be something like a web service request or some SSH traffic, something like that. And the way that IPv6 knows that this is TCP data is that it takes a look at a field that it calls the next header field that I've abbreviated here as NH. The next header field says 6. Now, if we had spent some more time going through the IPv6 headers, you would see that the next header field is comparable to the protocol field that was used in IPv4. Remember in the first lab when we looked up the IPv4 protocol and we found it was 17 for UDP? The other value for TCP is 6. So if you saw 6, you would know that the data that follows this header is TCP data. So how do we use this authentication header? How do we put this information in here such that we know that all of this data has been authenticated as coming from a particular place? Well, what we do is we split the packet right here and we insert this authentication header. Okay? The authentication header now gets its next header field updated to point to TCP. So it now knows that the data that it's carrying is TCP data. But you'll notice one other thing that happens. Up in this case, the network header was 6, indicating that the next bit of data was TCP. Now we're going to change that so that we say that the next header is not TCP after all. It's actually the authentication header right here. And its value is 51. So I can look at this packet and say, okay, well, here's an IPv6 datagram. Its next header is 51, which means that it must have an authentication header in it. Its next header is 6, which means that this data must be TCP data. And furthermore, I can use the authentication algorithms to authenticate this whole packet as coming from the address that is the source address in this header. This, by the way, is referred to as a transport mode. There's 2 different modes, and it's not really important that you understand the distinction at this point. But anytime you take a header and you wrap it around what was originally the data part, you're doing something called the transport mode. This actually should say ESP right here because this is datagrams with ESP. So again, I've got my IPv6 header. The next header is pointing to TCP data. So now what I want to do is I want to wrap this data in not only some authentication but some encryption too. So I want to make it unreadable. So I take this, I split the packet here, I put this ESP header in there. Its next header field is 6, meaning that it points to this TCP data. And you'll notice that the ESP also tacks on this trailer here, which has some authentication information in it. So you can kind of think as like a wrapper or like a box that goes around the whole thing. And now I need to put my IPv6 header in front of this one. But my IPv6 header next header field is now 51, indicating that its next header is an ESP value. So again, if I were looking at this in Wireshark, I could say, okay, well, its next header is 50. That must mean that we're looking at an ESP header here. Its next header is 6, which means that this data, even though I might not be able to read it, actually contains TCP data. Now, I have these lines here on the bottom to indicate a very special thing. Not all of the packet is encrypted. When we do this particular operation, the only thing that we really encrypt is the original TCP data. We don't actually encrypt the ESP header. Why don't we do that?
It has to be read.
The routers have to be able to read it, right? So if I encrypted it, then the routers wouldn't be able to do anything with it. So we leave that unencrypted. But what do we do with the authentication portion? most of the ESP header is in fact authenticated. So we can say that this is authenticated. Actually, that should include the IPv6 header too. I've got to do something with this slide. But at any rate, so we have a portion of the packet that is encrypted because it needs to be, and then we have a portion that's unencrypted because it needs to be, and then we have a larger portion of which is all authenticated. Here's some stuff that we didn't talk about. You know, the sad thing is again, I say this to my students all the time. I wish I had twice as much time to spend with you because there's just so much to tell you about IPv6. We didn't talk to you at all about mobile IPv6, which is a whole set of protocols that allow devices with limited capacity, limited memory, limited CPU, limited radio frequencies and power to actually operate in an IPv6 environment. We also didn't talk about routing table efficiencies. One of the things that is a big payoff for IPv6 is that the routing tables now are much smaller than they used to be with IPv4. And the reason is again, because we have this contiguous space of addresses. So now instead of maintaining a set of addresses and a class label, or maybe something else called a CIDR addressing, we just say, hey, if you see this prefix, it goes to Syracuse University. If you see this prefix, it goes to Purdue. If you see this other prefix, it goes someplace else. So you're seeing that routing tables are being lowered by an order of magnitude, which is significant if you have to go through all of those routes to find out where a particular packet goes. We didn't spend not nearly enough time talking about these IPv4 to IPv6 transitional technologies. There's actually a couple of captures that I've included, and I had hoped to get to one of them. John and I talked a little bit about one earlier, this idea of 6 to 4, so you can have IPv6 operating on one network, and when the traffic leaves that network, it becomes IPv4, and then there's something on the other end that will convert it. And we also didn't talk about all the enhancements that have to take place to something called the domain name service. Whenever time you look up something on the internet, the first thing that happens is that it converts this textual name that is easy for human beings to understand, like www.oswego.edu, into some sort of IP address. And so all that has to be modified in order to handle IPv6. This is timely. So this was on Monday. By the way, the ARIN is the American Repository of Internet Numbering. So it handles all of the requests for internet addresses in North America. Actually in Latin and South America as well. So they released a statement on Monday, a week ago, that said they have they're formally letting all of these CEOs know of these various ISPs that we don't have any more IPv4 addresses to give you. That within the next 2 years, they estimate, we will be out of IPv4 addresses. The last sentence is telling us, says, after that, organizations that need additional IP addresses will need to adopt IPv6, a new version of the Internet Protocol that provides a much larger pool of address space. So now they're actually telling people, hey, this is serious. We don't have any more of these to give you, but we have addresses in this big other pool that are just sitting there, and if you want to use that, we'll give them to you. You may be wondering, what's taken so long? Why is this such a problem? People do hate change, and there are a lot of reasons. We have been wrestling with what to do about IPv6 for now 11 years. The standard was named in 1998. I had just started graduate school when this particular standard had been adopted. And if you were to take a look at all of the traffic, it doesn't matter what country you go to, it doesn't matter whether or not it's a huge country or small country, big address space or small address space, it's typically less than 1% of all the traffic that you see. So why is that? Well, a lot of people say, well, it's too technically difficult to handle this transition. Everything seems to be working fine as the way it is, but I just don't have time to devote to re-engineering my whole network for IPv6. There's also a perception problem. We in the United States have the luxury of owning about 70% of the IPv4 address space. A lot of people don't realize that. So the United States has 70% of the address space. The rest of the world has 30%. So for us, we have all the addresses we need. What are you all complaining about? We don't understand it. So in this country in particular, there is this perception that there isn't a problem, kind of like climate change. But the issue is that we can't grow. That's the problem, really, is that we've got all these addresses, but we don't have any more. We know that we're going to reach an upper bound. Another problem, of course, is education. I am so pleased to have the opportunity to speak to you all, because I feel like doing that will then sort of extend my reach to a lot of students who should hear about this, that it's coming, and they need to be. It doesn't matter if you're writing applications, it doesn't matter if you are putting networks together or supporting. You have to know how IPv6 works, because it's basically here. The bottom line is that everybody has to know about this stuff, and they have to know about it soon, because our students are the ones that are going to be entering into this transitional period where they're going to be expected to be able to handle networks that are both IPv4 and IPv6, and be able to handle the transitional technologies that exist. And it doesn't matter if you're writing applications, if you're supporting the network, you have to know about this stuff, because this is the future.